Right, guys. So good afternoon and welcome back to the series of the deep learning, machine learning, NLP, and computer vision. I hope I'm audible, guys, and you are able to see my screen, right? Just give me quick confirmation before we start. Okay, all right. So, guys, today we'll discuss very super important concept. This concept is very important. First concept will be obviously vanishing gradient descent, and the second concept we will discuss is the exploding gradient descent. So what is vanishing gradient descent? What is exploring gradient descent? And on top of that, we'll try to understand when we saw through the machine learning process, we also try to understand that sometimes machine learning algorithms also overfit, right? We saw visually that what does mean by overfitting and what are the solution for the overfitting, what is the meaning of the overfitting. And same thing could also happen with the neural network. So what if the neural networks gets the overfitting, then what all the solutions are there, or how the actually overfitting look like, what is the solution, and how we can implement the overfitting, that is called as dropout layer. So these are the three main concepts, guys, and once we understand this concept, we'll move to the practical. I will make a code walkthrough. What we'll do is we'll try to set up one small neural network. We will be the architect of this neural network. As per our choice, we will develop this network, and then I'll make you go through that how this neural network works upon. So maybe we take a case of the bank churn model. So where the bank customers are leaving the bank. So let's try to analyze or predict that who are the customer who will be leaving the bank in coming months. So and that will be the first project we'll look upon. Then I will switch to maybe I will do this with the Kaggle and then Kaggle notebooks. And then second project, what I'll do is I will take unstructured data in form of the image and we'll try to identify the image. Let's say this will be first case will be of the binary classification, and the second case will be for the multi-class classification, where we'll try to identify the handwritten digits, picture of the handwritten digit, and let's see if we whatever neural network we will create, whether this neural network will be able to identify the handwritten digit or not, right? So I guess the agenda is pretty clear, everyone. So almost most of the participants are here. So I wanted everyone to attend this session because this is super important. Once we understand this concept and when we deep dive into the practical, so you guys can relate whatever things you have learned, that how the neural networks is formed, what is forward propagation, what is backward propagation, what are the activation function, loss function, optimizers. We also understood how the optimizer is, right? How the optimizer is working, what are the optimizers, which one is the best, and what is how the weights are actually getting calculated, and the super important topic of the chain rule, that how the chain rule is helping us to update the weights, right? So without wasting time, let's get started and try to understand that what is the issue, what is the vanishing gradient problem. So in simple terms, when I talk about the vanishing gradient descent, the problem history of how this vanishing gradient descent came into the picture is during the we understood that we also know now looking at the history that first neuron model was built upon by the Makello and some other gentleman in 1950s, and this was a single model. Then they developed the perceptron where they are adding multiple neurons. Then they came up with the hidden layer and all. And then until unless our godfather of AI, Jeff Hilton, he introduced the back propagation, and then everything started working fine. And they started using different activation function and loss function, and the things were going smooth. But one problem was happening is when people started introducing the hidden layers. In terms of the hidden layers, a depth neural network, let's understand in this way. Depth neural network means the hidden layers which are present in the neural network will be around more than 100 or 200 or some sort of this kind of architecture, where there will be many huge architecture will be produced in order to analyze or solve the complex data, right? At that time, what was happening is these deep neural networks, when they creating this deep neural network, they were using the sigmoid function as an activation function in all the layers. And due to this activation function and the process of the weight update, they were failing somewhere, right? So there was an issue. I will try to understand what was the issue and what is happening. But they were facing issue when they are trying to create this depth of the neural network and try to identify the patterns. And that was mainly caused by the updation of the weights. And what was the main reason? This is the combined effect of the sigmoid activation function and the weights. Because we are trying to update the weights, at that time we are trying to take the derivative using the concept of the gradient descent, right? So let it be gradient descent or stochastic gradient descent, Adam optimizer, or the SGD, that is stochastic gradient descent with the momentum. But they were facing issues, and that facing issue was related to the terms of the weights and again the activation function. What was happening? What was the issue? Issue was that, as the name suggests, the gradients were vanishing. What do you mean by gradients are vanishing? Is whenever we are trying to update the weights, we are trying to take the derivative of the loss function, right? We are taking the derivative of loss function with respect to the weights, right? This is what we learn. Whenever I am trying to update the things, I am taking the derivative of loss function with respect to weight, and then I'm calculating the new weight, right? If I'm calculating new weight, I'm taking the old weight minus eta, which is the learning rate, multiplied this loss, right? Derivative of loss function. And what was happening is this, by every iteration we saw neural network, right? That whenever we are doing a back propagation, right? Whenever doing back propagation, this was the forward propagation, and then we were also doing the back propagation, right? The back propagation in this direction, right? At that time, we were updating, right? This process was going from forward propagation to back propagation. We are trying to update the weight. This was one iteration, correct? This was happening for first time when the weights are updated. This was happening in simultaneously in the batches, right? Again and again and again and again and again, till the time we are able to optimize our parameters. What are our parameters? Weights and biases, right? So that is the work of optimizer. So this iteration, or let's say epochs, were happening, and during these epochs, what was happening, when I have a depth of the neural network, my weights were not getting updated properly. That was the issue because of the loss function. Because whatever loss function I was calculating, this loss function derivative was very small. The number was very small, and let's say 0.04. This derivatives result was very small, and I will also try to explain you in detail like why the derivatives will try to calculate, and I try to tell you that why the number was getting small. And whenever you are trying to apply the, let's say learning rate is 1 and the old weight is 5, and this is the new weight you are trying to calculate. So whenever you are trying to apply, obviously in this new change, this will be 0.25, right? You try to understand. New weight will be 0.25. So there is not much change, right? There is not much change in the weights. So this way, what happening is there was this, one situation was occurring where after multiple epochs, the old weight was exactly equal to the new weight. And this is where the learning was getting stopped, because until and unless we are not able to update the weights, how the learning will happen and how we'll be able to optimize our parameter. That was the issue. Okay, so you guys now understand what was the issue. What do you mean by vanishing gradient descent, right? So vanishing gradient descent has to do with the derivative of the loss function and the kind of activation function, which was sigmoid, which they were using. Because of that, the old weight and the new weight was almost same after some iteration, and due to this issue that the weights are not getting updated, the neural network was also not learning after a certain epochs or certain times. So there was no change in the accuracy. So that was the main concept behind it. So just for the funny purpose, I have taken these two pictures. So in vanishing gradient descent, the weights are getting less and less, right? Not weight, actually the loss derivative of the loss function, right? Derivative of the loss function is getting smaller number, right? Getting small, and because of that, the weight changes are also not prominent, and weights are getting less. In the way, it is also affecting the weights. So that is how the vanishing gradient problem was. In exploding gradient descent, exactly opposite side was happening. Exactly opposite. The weights were getting too high. Okay, weights were getting too high, that the difference between old weight and the new weight was very huge. Okay, it was very huge, and because of this huge weight, let's say if we also understood yesterday, if this is negative slope and this is positive slope, and this is the picture of the gradient descent where I am trying to reduce my loss, and this is my weights and biases. At that time, this is the my minimum point where I have to reach, because I have to make the derivative 0. Right? We will get the attendance after end of towards the end of this session, right? So usually the same way we get the same way we every day get the attendance, at that time only you will get, and don't worry about the attendance peak and everything. So try to concentrate on the link, okay, on the session. Sorry. So what we were discussing is that whenever there is a huge difference between the weight, let's say, and what is my aim? I have to move towards this minimum point, right? I have to move towards this minimum point in such a way that I have to adjust the weight. I have to adjust the weight and I have to adjust the loss function accordingly, and I have to optimize these two parameters, right? The weight and the biases. So if let's say this was my W1, weight 1, old, and if I am giving it was somewhere here, and all of a sudden, if I am giving new weight somewhere here, right? So it is a huge jump, right? And again, there is a similar jump, then maybe it goes back. Let's take different color to understand this one. So if there is a huge jump from here to here, and again from here to there, this way it will keep on rotating, right? So there will be huge on, let's say there will be too much variation, right? So at times you will get a too much variation in your results, and you will not be able to reach to this point very easily. And this point is the point where we are getting derivative of loss function with respect to weight equal to or almost equal to 0. That is our main aim, because we have to reduce the difference between actual and predicted, right? So that is why we are doing this one, loss, reduce the loss. And that was the issue with the exploding gradient descent. Let's try to understand, go in detail and try to understand what are the things happening when we try to calculate the weights. Correct? In this case, we'll never reach the minima. Yes, guys, we'll reach the minima, but it will take too much time, because if I am adjusting the weights in like, let's say the difference between weights is too much, then there it will be difficult, right? Then I have to, if usually a model running for, let's say, 1,000 epochs, let's say for 1,000 epochs, this 1,000 epochs will not be sufficient, because I have to give also learning rate. Learning rate is the way how it jumps also, right? Along with it. So I can control somehow by using learning rate. Learning rate are usually very small. So I can control this weight amount of weightages. Let's say it is 500. I can control that, right? That's why we are using learning rate multiplied by this derivative of the loss function. So that is the sole purpose also, to introduce the learning rate. So this kind of situation can be taken clear. So I hope, guys, the overview about the exploding gradient descent and vanishing gradient descent is clear. So if in short, I want to summarize what is happening when there is a vanishing gradient descent, weights are getting small, they are vanishing. Simply try to understand this way. They are vanishing, right? And whenever I try to update the weights which are getting larger and larger, at that time they are exploding. That means exploding gradient descent. And this one is vanishing gradient. This is vanishing, this is exploding, small and large. That's how, guys. And we also try to understand what was the issue, that whenever we trying to talk about this, what was happening, why we are getting this kind of situation, or what will happen if we try to take the larger weight. Try to understand similarly. I will try to draw a simple neural network, and at that time we'll try to calculate the loss function, and we'll try to understand in detail, like what could be the situation. And why the sigmoid function is behaving in this way, that is the main reason why we are trying to have this vanishing gradient problem and how to control it. So let me draw again our favorite neural network, which consists of the 3 inputs, which are going into the hidden layer. Let's say these are 2 hidden layers, and then we are getting a output. So this is a simple neural network we're trying to understand. And on the basis of that, we'll try to calculate the weights and try to understand the things. So this is my x1, this is x2, and this is x3. Right? This is weight number 1 1, because this is the first layer and first weight. And then let's say this is my hidden layer, and then after that hidden layer, here I am getting output as O1, 1, 1. This is O11, correct? And here, then after O11, I am getting the output here as O21, correct? And similarly, we have other bits as well. This is, let's say, O12, and this is second layer after that output layer. This is where we are getting our Y hat. This much is clear, I think, guys. This is our final output, and this is O11. Okay, let me write clearly. This is output 1, because what will be the output? 1, 1, and this is output 1, 2. So what is happening here? Two-step process, summation of inputs and weights, right? Along with the bias. This is what happening here. And it is going into the activation function. And then it try to give me the result, right? So this is what is happening inside these neurons. So what I want to do is now, I want to calculate the new weight for W11. Let's take a look. So I want to calculate weight for W11. So what will be the formula? Again, it will be same. I understand. The formula, I will try to write a formula over here. So if I want to update weight 11, usually this is the new. I'll write as a new. So formula will be weight 11 old, right? Minus eta multiplied by derivative of loss function with respect to the weight. So we also understood by using chain rule, right? By using the chain rule, that whatever weights I'm trying to update, this O11 will be dependent on W11 will be dependent on O11, and again this O11 will be dependent on the final output, right? That's what we try to understand. Let's call this final output as O21, correct? So what I'm trying to achieve over here is, let's use the different color. So I am trying to achieve this path from O211 prediction. I am going back again in back propagation till this weight O1 W11, and this W11 now I have identified that this W11 is dependent on what? W11 is dependent on what? It is dependent on O11 output of previous layer, and also previous to previous that layer, right? Also output means everything, guys. Whatever weights will be here, right? Again, I have to update. So for the combination of weights and biases, I'm taking this as output O1. Okay, don't get confused. So I will write the formula. I will try to break this derivative again in further. But how we can break this derivative and try it in further terms. So let's take this one. Derivative of loss function with respect to D11. So I can again write it, since I understood that it is completely dependent on what? Previous layers outputs and weights. So let me write this as O21, this one first, O21 divided by O11, this one, right? First I will try to go from here to O11, then again multiplied by derivative of O11 with respect to what? With respect to W11, right? This is how it will happen, right? In chain rule. So I can split this further, that because my W11 depends on O11 and O21, all the previous outputs, and these outputs include the weights and biases. So I'm not trying to write it again. Okay. So try understand. So I have to update the weight W11, and this is how we will encounter the vanishing gradient descent. Okay. Try understand this one. So what will happen is now, since I am using the sigmoid activation function, correct? Like, let's try to understand now sigmoid activation function. Activation function which we were using here was sigmoid, correct? Let me use the different color. You guys can understand. Sigmoid activation function. And what is the formula of sigmoid activation function? Sigmoid activation function, right? Sigmoid activation function will be given by 1 divided by 1 plus e to the power y. And y is nothing but weights and biases, weights multiplied by inputs plus biases that we have seen already here. Okay. So this is my activation function, and this is activation function means with respect to this activation function, I am calculating the loss and taking the derivative with respect to the weights. That's what is happening. In terms, I am taking derivative of this sigmoid function only when I try to understand in detail. So what was the issue with the sigmoid is, let's say, let me plot the graph of the sigmoid, so we can understand what is the issue with the sigmoid. So my sigmoid function will look like something like this, which will be ranging between 0 to 1. It has a range between 0 to 1. And let's say these are the negative scale. And this is negative. This is positive scale. Let's say 1, 2, 3, 4, 5. And this is negative. The sigmoid function will always be lying like this. Right? And let's say this is somewhere 0.5. This is our threshold. If the value which is given greater than threshold, maybe it will pass or it will not pass. So this way it will try to activate the neuron or it will not activate the neuron. That's how we understood, right? So when the problem will arise when we are using the activation function. At that time, we are trying to take the derivative of the sigmoid. Let's say if I try to take the derivative of the sigmoid function, right, with respect to z, because I am considering z as what? Activation function y followed into the activation function. So whenever I am trying to take the derivative will always lie between 0 to 0.25. That not from theoretical perspective, guys, try to understand from practical perspective also. If you try to calculate the derivative for this formula, right? For this formula, it will always give you, this is minus, this always give you a derivative between somewhere between 0 to 0.25. Trying to understand from graphical perspective also. So that means it will lie somewhere, if this is my 0.25. So it will start from here and it will lie here only. So why I am telling you all these things, okay? You will understand that why I am taking this maths class. But because we need to understand that we are updating weights. In order to update weight, we are taking derivative of the loss function, and loss function is using the activation function itself within it, right? So if I taking the derivative at that time, my values will be most probably lying between 0 to 0.25. So I understood now, whenever I take the derivative, it will lie between 0 to 0.25 for the sigmoid function, and then try to input the same thing going back into my chain rule, right? So this is my chain rule. If I am trying to take the derivative at the different stage, at that time, what will happen? If I take a derivative for this output delta of O21, which is here, right? This O21 divided by with respect to O11. At that time, the value will come somewhere between, let's say, 0.2. Randomly, I'm taking value because it cannot be more than 0.25, right? Whatever derivatives we are taking, it will always lie, whatever derivatives we are taking, it will always lie between 0 to 0.25. So first derivative you took for the first output, which includes the weights and everything, biases, and it came around like say 0.20. And then second derivative which you will take in order to update the W11 will be O11, right? Output O11 with respect to the these two things, right? Respect to W11. So let's say again that value came somewhere around 0. Again, it will be raised, right? It will be like whenever I take a derivative out of derivative, again, whenever I'm trying to take the derivative, the value will get less, right? It will get reduced. So that will be again less, because after taking derivative at first stage, I am again taking derivative at the second stage, and then I'm trying to reach to W1. That's how. So that's how if I calculate this final product, what will be the value? Let's say 0.04. As approximate I am taking, don't quote me on the correct value. So what is happening? My derivative is coming, loss derivative is coming with respect to weight 1 is around 0.2 sorry, 0.04. 0.04 was the derivative. So again, let us calculate again. Okay, let's go back to our formula, this formula, and try to calculate. Just I will replace this value here and we'll try to calculate the new weight. So I want to calculate the new weight. So let's take example that the old weight was somewhere around, let's say 2.5. Okay, this value W11, this is W11 old weight, right? Let me denote it by a different color. This was the value of W11 old, which is 2.5. And now minus eta into this loss function dl by dw1, which I have calculated, which is coming to 0.4, 0.04. So if I multiply this again, right, in order to calculate, so what will happen? No, not 0.04. Let's say this is somewhere around 0.2. We'll take initially less. And if I try to put in here 0.2, okay, 2.5. Let me write it again. Okay, we'll take less value. Let's say 0.2. If I multiply this, let's understand that derivative is coming to 0.02, not 0.4. Okay, at times. So I'm taking less values. So this is the final product approximately, right? Not let's say hypothetically it is coming to 0.02 and my old weight was 2.5. Old weight multiplied by the learning rate, let's say learning rate was 1, and 1 multiplied by again 1 into 0.02. So if I calculate this, what will happen? It will give me very less value, right? Somewhere maybe, I don't know, 0. Not 0.2 point around, right, correctly. If I perform this multiplication, 2.5 multiplied by 1 into minus 1, sorry, into 1.02, the value will be somewhere around, let's say 2.46 approximately, not exact value, but somewhere around 2.4 or 2.46, right? So what happened here? New weight is 2.46 after even performing the calculation, all weight updations, and the old value was 2. So if you can say there is no much change, right? Whenever we calculated, we saw went through the iteration by iteration. We did a dry run, right? We did a dry run in order to understand, correct? In order to understand, when I try to update these weights this way and take the chain rule. So if I initially taking the sigmoid function is giving me the values of the derivative, which is between the range of 0 to 0.25. And because of which, if I try to adjust the formula accordingly, the old weight and the new weight will have not much difference. That is, old weight was 2.5. And if I calculate by this formula, new weight will be 2.46 or somewhere 40, somewhere something like that, right? So I don't see any much difference. If there is no much difference or much change, right? So what is happening? Again, this is the gradient descent. This is loss function, right? Let me take another color. So from here, this old weight, I am trying to go down, right? Because I have to reach to this point. If I am trying to go down and there is no much change, what will happen? The new value will be only here, right? There will be not much change. So layer by layer, if I am going, they should adjust, right? I should try to reach to the minima. So it is like taking too much iteration, like it is moving somewhere like this, and then after so many iterations, maybe this value will become exactly equal, or there will be not much change in the old weight and the new weight and the old weight. Sorry, vice versa, right? New weight and old weight will not be a much change. So in order to reach even minima, I will take the time and will not be able to give you. How do you update if more than two connection connected to W1? Yes, yes, the same backward, same way again. Whatever I have taken example. So we'll try to bifurcate again. We understood that we'll also add many connection from here, and the process will be same again. Same way it is trying to update the things, but the whole idea in order to understand the vanishing gradient descent is that whenever I am trying to update the weight, and because of the gradients derivative which I am taking of the loss function, and especially the activation function, the values are very less, and the changes between the W old and the W new is very less, and because of that, and one time it may become similar, and once the weight becomes similar, my neural network will stop learning. So that is the whole idea, guys. So we understood from graphical perspective also, and from the theoretical perspective when I calculated the weights. So there is not much change, right? So that is why if there is not much change, no much change in both of them, so there is what is the use of the weight updation? Why we are updating the weight? In order to reduce the loss. So if there is no change in the weights, there will be no loss reduction. So that is the entire concept of the vanishing gradient descent, guys. I hope you guys understood this one. This was simple. What we did is, just to summarize, we tried to calculate using the chain rule the different loss function, derivative of the loss function, and we tried to go back and update the values accordingly using the sigmoid activation function. And we saw using sigmoid, it was only giving us only values between 0 to 0.25. So which was in terms affecting the loss function, and this was afterwards giving an effect in the weight updation. New weight, not much difference between the old, and the learning or loss reduction process stops. So that is why vanishing gradient descent algorithm should be taken. The problem should be solved, right? And what is the problem? I hope everyone is now clear what is vanishing gradient descent and why it is happening. We saw from graphical perspective also, from the theoretical perspective also, from the mathematical perspective. So what is happening? So we try to understand if what is the science, that how you can identify that your neural networks is having vanishing gradient descent. So what could be the possible way? Maybe your model stops learning. What do you mean by model stops running? So epoch by epoch, whatever loss you are having, but let's say loss value is around somewhere 10%. Even after certain epochs, you will not see much change in the loss. Maybe from 0.10, it is become 0. Let's say 0.09, somewhere, not much difference, right? 9 or somewhere around it, right? So not much difference, or maybe it is constant. Even after further iterations, it is remaining at the 10%, not reducing even to 9% or 10%. It is stagnant. So that is one of the let's say signs that the model is not going down. Model is not learning. It is not reducing the weight. Okay. So just even after some epochs only, you will come to know, when we try to do it practically, that when I will try to run the artificial neural network in front of you guys, then you will understand by every epoch how the accuracy is getting calculated, how the loss is getting reduced. At that time, maybe you will try to understand these things more accurately. But try to understand, whenever I am doing epochs mean iteration. What one iteration will be of entire life cycle. Forward propagation, going back, calculating the loss, then optimizer, and again backward propagation and updating the weights. Again, new predictions. Okay. At the times, the weights are not getting updated, or weights are becoming zero, almost zero. So my model is not learning, or showing very significant, or the weights near the output layer shows significant change, while the weight near the output layer showing significant change, while the weights near the output layer may not show at all, no change at all. What they're trying to say over here is, let's say when I'm trying to calculate, right, this is my neural network, and I have certain layers, right, hidden layers here. Let's say more than one hidden layer. So when I'm in back propagation, right, while different color for batch preparation. And this is in turn giving me the output, right? This is my output layer. So let me use different color. When let's say this is layer 1, layer 2, layer 3, layer 4. So when I go back during the back propagation, right? I try to update these weights, these weights, and the weight difference between W3 layer and the layer 3 and the layer 4, whatever the difference is, that is not significant. That means the weight layer at the let's say layer 4 weights were like around 2.5. Okay, and if I going around the weight layer 3, the weights has only become 2.45. So there's not much change. That's what they're saying. If I see that there is not much change in the weights, right? The weights are not changing. The weight should not change very drastically, and it should not change very small amount, right? It should be optimal. That's why we are using optimizer. So that is the main difference. They're saying that whenever I am trying to go back layer by layer, layer by layer, so there should be a change, significant change in the weights. If there is no significant change or showing no significant change, at that time you can understand that my model is having is facing the vanishing gradient, right? And we also stop about after certain epoch. Let's say if I am running my model for 1,000 epochs, after let's say reaching to 600 epochs only, after 600 epochs only, my loss, let's say, is stagnant at 10%, and throughout the next iteration, after 600 iteration till it reaches to the 1,000 iteration, it is not reducing, it is staying stagnant, right? So that could be one of the sign or symptoms that I am facing vanishing gradient descent. And similarly, guys, when it is exploding gradient descent, I will try to explain again in detail. So whenever we are facing exploding gradient descent, at that time also the weights layer by layer, which let's say in this layer the weight values, let's say 500, and again it is drastically going to 300, again 200, very huge difference, right? So that means my weights are exploding. They're exploding, the going anywhere. And again, why all these things means, try to understand from gradient descent of point, from this value to directly jumping here and there and here and there and here there, very huge difference, variation. And then main aim to reach to the zero derivative will be lost somewhere in between. Or they can say the model is not trained to learn anything because of the huge variation. What happens is if you try to change very quickly, so it may pass the global minima, it will not reach the minima. That is the point. So if it's quickly changing, so some step or some iteration which are very significantly slow required at certain point of time will be missed. So you will not able to reach to that 0 point. So that is the whole idea. That's what they are trying to say. Let's try to understand that how to handle them, right? So there's a different methods given, right? Try to understand what they're saying. Whenever we are switching using the layers, maybe what you can do is rather than using 100, let's say usual misconception among the people is, if I use a high hidden layers, whenever we try to calculate the or create architecture, people understand this way that hidden layer performing some kind of magic. So if I take, let's say 100, 1,000 or more than that hidden layers, then it will create a magic and then it will be able to achieve the exact prediction what I am expecting. But that is very misconception among the people, right? So if you use a hidden layer, again, we understood that when we doing a back propagation, going from layer by layer, weight updation will be very slow or will be very negligent, because in terms the weight updation difference will be very less, because old weight will not be much different. It will be almost similar to the new weight, and old weight will be almost similar. We've seen, like using the derivative and the calculation. So there will be not a significant change. If there is no change, my network is not learning again. Network is not learning. It is not learning means, if it is not learning means loss is not getting reduced. Again, loss is not getting reduced. So that is how it is interconnected. So what they say is, when we are trying to create architect, at that time only use less number of layers. Because if you use more number layers, you will get somewhere vanished between the layers and your weights will also get vanished. And the second thing what we can do is weight initialization. Okay. So whenever we are doing the weight initialization at the first time, people try to take the random weights, or there are certain other methods also. Like I told you, we can do a hyperparameter tuning, or we can use any mathematical concept. So how to choose the weight again initially. So people usually say that the initial weight, whenever we are initializing the weights on the first iteration, that is taken randomly. But again, we'll try to understand some point of time that it is again not random. Okay, that process people say is random, but it is not random. It has some certain calculation with it. So maybe we have to be very careful when we first time try to initialize the weights. Second thing what we can do is we understood entire problem was coming because of the function, activation function, which we were using, sigmoid like function, which was trying to give us a value between 0 to 1. And if I take a derivative, which was giving a value of this derivative between somewhere 0 to 0.25. So we have to, if I see that sigmoid function, mostly people were using sigmoid function at that time when they trying to create this kind of architecture. So maybe I have to choose my activation function in such a way that the new function called as ReLU, which we understood, right? And the graph of the ReLU look like this. The formula is like for ReLU is max of 0, comma x. X is actual value, whatever value you have, max of 0 and 1. And the graph will look like something like this. 0 because this is 0 and 0 to this one. So this is ReLU, normal ReLU. Again, there are different rectified linear unit, guys. ReLU function is rectified linear unit, and this ReLU function is become very popular once they realize that this sigmoid function has the issue of the vanishing gradient descent. And that time the ReLU function become very popular, and they started using the ReLU function, and because of this ReLU function, they were able to take care of the vanishing gradient descent. So what we have to do is whenever we are choosing layer by layer, every layer we understood that the neuron is performing the activation function. We are trying to sum, we are trying to take a sum of all inputs and the weights. This is called as Y. And in step 2, it is going through the activation function, and which is called as Z. And Z is the output, which will be passed to a next neuron, right? So this is how the things are happening. And then whenever we are using the sigmoid function, primarily why we were using sigmoid function, to bring back the score, which were lying between minus infinity to plus infinity in the range of 0 to 1, to bring the non-linearity, and also to, in order to predict the probability, right? If I have to predict the probability, whenever I am not able to solve the situation using the exact, let's say, whole numbers, then in case of the movie ranking, we understood also in case of the sentiment analysis, at that time, if they are giving a very vague sentiments, we can even try to calculate the probability. On the basis of the probability, at least we will be able to say that what are the chances that these comments are towards the positive comment side or negative comment side. So that is the main reason why they were using this one to bring back this scores between range of 0 to 1. But again, it has certain its limitation when we are trying to do a depth of the neural network. So they people introduce the ReLU. ReLU again has the different flavors, guys. ReLU has again P-ReLU, right? P-ReLU, Leaky ReLU, right? P-ReLU, Leaky ReLU. There are again various forms, and there's the only small changes, like in Leaky ReLU, they are using like whatever is different, whatever is a max of 0.001 to max of 0.001, comma actual value. So these kind of variations are there. Exponential ReLU is there. Okay, P-ReLU is there. Parametric ReLU is there. Normal ReLU is there. So there are different variations of the ReLU function which is available, and we can use. The graph will be somewhat like this one only if we are using 0.1, and this is how it will work whenever you are using the different activation function. So what they are saying is you choose less number of layers, weight initialization should be done properly. Then when you are using the different activation function, try to analyze if you are facing gradient descent, maybe you switch to ReLU function or some other activation function which will be able to give you the value. Some tan function we also saw, which is giving you a value between -1 to 1, right? Tan function is again looking like this one, similar to sigmoid, but the value range is not between 0 to 1, it is between -1 to 1. So tan is also a good function. tan h, hypertangent function, guys, tan h. This is also one more function. The graph looks like between -1 to 1. So this is also option. So that's what they're saying is use different kind of activation function. Again, what this concept is very important, guys. This batch normalization. Usually, the batch normalization, what this says is when we are using the convolutional neural network, at that time I will try to go into the detail and try to understand what is batch normalization. There are two kind of normalization which is happening. Let's say if whenever, let's clarify everything. So I told you that whenever we are passing any picture, right? In convolutional neural network, whenever we are passing any picture, which is a color picture, right? So it is try to understand that as a matrix of 3, red, green, and blue, right? This is how it will try to understand the picture, right? Red, green, and blue. This will be red, this will be green, and this will be blue. And this will have a certain numbers, pixel numbers, right? Certain pixel number will be available on that, right? Pixel intensity, which will be between 0 to 255. All the pixel intensity are between 0 to 255. Let it be any color, and all the colors are made up of the RGB, right? Different combination of the RGB. So whenever I am trying to pass a picture and I am trying to take the layers, again, this picture will have certain dimension like 800 by 800 dimension of, let's say, 800 pixel by 800 pixel, and 800 by 800 pixel multiplied by 3, right? 3 matrices. At that time, when I am trying to apply the convolution, what do you mean by convolution? We understood that if I have an entire this matrix, I will apply small matrix on that are called as kernels, and I will try to extract the information using the bigger picture. So by you applying this small value, small matrices on the bigger matrix, I am trying to extract the features. Because what I have to do is I have to understand the feature from the image. If I am giving image, let's say you are providing an image of the Vikas, and the Vikas is a person who looks like this one, his eyes, hands, and so on. It's a very dirty picture, I can understand. It is not appropriate picture, but let's try to understand from the concept perspective that whenever we are trying to provide a picture of the Vikas, right? So Vikas will have different in the image. There will be different gradients and different outer lines will be available. One will be related to the face, one will be related to the body, one will be related to the legs and everything, right? At that time, this whole picture will be got filtered on the different regions, and I am trying to extract these features. I am trying to extract the different features, and I am trying to take the features, and on the basis of the again feature, I am trying to calculate new matrices. And then in the end, I will be able to give you the probability, right? The probability of the picture, that this picture belongs to Vikas or not. That is, we are doing a classification. So that was happening at that time. What happens is whenever we are trying to create these different matrices and trying to convolute them, means we are trying to provide the filters. At that time, normalization will happen, and the batch normalization, there will be two. The normalization usually will happen for the depth. For the depth means throughout the matrices one by one, or could be happen on the only surface level normalization. So at that time, we'll try to understand what is batch normalization and what is across the depth or across the surface. The normalization is there. But normalization trying to usually how it happens whenever we try to apply the normalization, it tries to bring the data between normalization, normal distribution, where try to bring the value between 0 to 1 or -1 to 1. So that is what the normalization means. So whenever we are having this kind of gradient descent problem, we try to normalize the data and again normalize the weights, you can say, and try to take the new weights, and then model will be able to learn. Right? So gradient clipping will not go into detail. That could be also one of the way. But almost I think we understood whenever we face the gradient descent, how we can solve them, right? Hope guys, hope everyone is now clear with gradient descent. Vanishing gradient problem, and what is the issue with the sigmoid function, how it is causing us, and why we are getting stuck in updation of the weights, and because of that weights from mathematical point of view also we try to understand what do you mean by vanishing gradient descent, and how to handle what are the symptoms of the vanishing gradient descent, and how to handle the vanishing gradient descent problem, right? Just quickly guys, ping me. Quickly ping me if you guys are able to understand this concept, so we can move ahead. Okay. So quickly ping me, guys. Just couple of people. If pinging, giving me confirmation, then I will understand that we are able to follow the same thing. What is happening over here? So I can move to next problem, exploding gradient descent. Quickly, guys, give me confirmation so we can move ahead. We have to also look at the code, right? How we can create our own structure. Yes, no, guys, something like that. Or you guys are not able to understand what is happening over here. Just quickly ping me if you're able to understand this one concept, vanishing gradient descent. I can see only 1 yes or 2 yes, guys. Ping me quickly. Yes, no, probably. I'll wait for 1 minute and then I will go ahead, guys. All right. Yes. Okay, couple of yes. Okay, I hope, guys, you are able to understand. I can understand this was somewhat complex topic, but I hope I try to make it as far as possible, very clear and simple. So let's move to our next topic. Before even we go into the dropout layer, we'll try to understand what is happening when we are having the exploding gradient descent with the same examples. So let's try and understand very quickly within 5 to 10 minutes. We'll try to understand what is happening actually. So let's say I'll draw a simple layer now, a very simple layer. I'll not try to go for the entire layers. And using that layer only, we'll try to explain you through the equations. Okay. Let's say so you guys are saying that it is completely new and not able to catch everything together, but the way you can able to get the know the concept is good. So what I will understand by using this, guys. So I can understand this is altogether new concept, but at least you guys are able to understand now somewhat at certain level. Whenever I say there is a vanishing gradient problem, at least you should be able to understand that when I have a vanishing gradient problem, my weights are getting less and less and they are not moving, and the difference between the old weight is and the new weight is not much. So because of that, my model is not learning, right? So this one liner or one liner summary, if you guys are able to understand, I think that will be more than sufficient for us to understand in this initial session. So maybe when you guys will try to implement on your own, at that time you will encounter this kind of problems. And while doing practice, I guess all the concept you will be able to connect to the dots. Okay, guys, it is always good if you can express your thoughts, or you can add certain comments, so I can understand that how the things is going. So at least Priya is at least able to tell us that what she is feeling. If couple of people, if they want, you guys want to explain, like, did you get the concept, or at least you are able to get the feeling, that get a hang of the feeling that why this gradient descent, vanishing gradient problem is happening, the main concept and everything, then that will be more than okay for us. You can ping, guys, simultaneously till the time I will try to tell you what is exactly happening in the exploding gradient descent. I can understand this concept is somewhat complex when we try to understand these things first time. But I was able to tell you from the graphical perspective, also from the derivative perspective also, when we try to take the derivative in the chain rule, that how it is getting into towards not getting the zero and why there was a no changes, right? So hope this much explanation was okay for you guys to understand. And anyhow, you guys are very smart. So from day one, you guys are able to catch all the topics. So hope this topic was also very, let's say, was not that complex for you guys. So let's try to understand. Whenever I am saying that there is exploding gradient descent, what do you mean by exploding gradient descent? Exploding gradient descent means my weights are getting very high, right? Higher weights, and because of which because of the higher weights, right? I'm facing the issue. What do you mean by higher weights? My weight old, and the difference between weight old and the weight new is very high or very huge, and because of that I'm not able to reach to the minimum point. So let's say this is the minimum point for the 0. This is my loss function. So I'm just moving fastly from here and there because of the huge difference, and I'm not able to go to the bottom where my derivative is 0 with respect to loss function and the weight. So that is the main, let's say, main concept of what is happening over here. So I will try to rub these things. Okay. And I'll try to understand quickly within 5 minutes that again what is happening when I'm talking about the exploding gradient descent. So let's try to understand. This is my input. Okay, x1, which is going in this layer. This is input layer. Maybe this is my first layer. Weight W11. Let me write it clearly. This is weight 11. Okay. Then it is passed again. It will be giving me output like 011. Correct. And this will be somewhere like passed to the next layer, which will be giving me the output. Let's say layer 21. This will be second layer, right? This is O21. O21. Okay. And this will be my final output, right? So what I can understand is, and this is again connected, this O21 is connected, and here is my O31. So, okay. This is output 11, output 21, and this is output 31. Okay, and this is my initial weight. So what we have to do again? We have to update the weight. So how I update the weight? We have to again update the weight, right? We understood we get output y hat. We calculate this y hat with the actual. We try to calculate the loss. Y actual minus predicted. We get a loss. If this is like 1 and 0, the difference will be very huge. So my optimizer will come into picture. I will pass this to the optimizer. Let's say gradient descent, and it will try to go back now, right? Let's use different color. It will try to go back, right, from this direction, trying to go back. This is the going back again to calculate the weights layer by layer, right, to the back propagation. Within the back propagation, I am trying to update the weights. So let's go back and write our formula, how we can update the weight 11, right? This is what the weight we're trying to understand or update. The formula for the new weight was like W11 new. Again, same formula. There is no change in formula, like old W11 old minus beta learning rate multiplied with loss function with respect to weight, right? This was our formula. So what is happening over here is now, and again I will write a chain rule. I have to write a chain rule that if I want to calculate using the chain rule, the weight 11. So again, what I have to do is I have to write this derivative, and I have to expand this derivative, right? Let me write that derivative and expand it for you guys. DL by VW1 11. Again, like we spoke about, right? If I want to update W11, I have to take the way all along from the output back to W11. Taking that weight, I will encounter first output 31, then I will encounter up to 21, and then it will be updated, right? There will be two-step process. So let me write that one. The formula, right? D by O31 first output divided by O21, the second O21, then multiplied by, right, O21. Again, O21 is dependent on, O21 is again dependent on what? O11, O11, right? And again, this O11 will be again, this O11 will again go back to W1, correct? All right, multiply by D O11 divided by D W11. So again, same thing, guys, what we are trying to achieve, right? If you cancel these terms, right, if you cancel these terms, right? So again, you will be left with the same formula, which will be like DL by D11. So I am just trying to expand this derivative in terms of the path we are taking when we are doing a back propagation right from the output layer, that is output 3.1 to output 2.1, from 2.1 to O11, again O11 to initial weight when I took the initial input. This part is clear, I think, right? So what we are trying to achieve here is, I have to update when I am trying to update the weights, right? When I am trying to update the weights, I have to update all the way through these outputs and this initial, let's say, weights and biases, because every layer there are weights plus biases. So that's why, in order to not to make it more complicated, I am not writing in terms of the weights and biases. Again, this equation will become very huge and we will get lost somewhere in between. So what I am doing is, I am just trying to take this notation as O11 in terms of the output. Okay, in terms of the output, I am trying to take the notation that whatever weight W1 is there, it is dependent on all three chains. This is chain rule. This chain will include O31. This is third layer output, then second layer output, and the first layer output. Okay, third layer output, second layer output, and this is what the derivative will happen. First time this will be the derivative, second time with respect to O21, third time with respect to O11, and then we'll be reaching to W11. That's what we are trying to achieve here. So when I am saying that I have to take a derivative in this fashion, so what I can do is, I can write this O211, this term, okay, separately. So let's say how I can write this O211. O211 is what happening at this level, O211. O211 is here, right? This is O211, right? This is layer 2, 1 output, O211. So O211 will be always consisting of what? Weights and biases, correct? So O211 is a function, let's say, is a function of the weights and biases passed to the activation, correct? Passed to the activation. So in this entire term, if I say Z, so I can say that entire term is passed like this one. Initially we have Y, right? Summation of all inputs and weights plus biases B, correct? Let me write in different colors so you guys will be able to understand. Initially, when I calculate Y, so it sums up all the weights inputs, multiply by weights plus the biases. At every layer this is happening, you understood? At every layer this step 1 is happening, right? Step 1 is happening and step 2 is happening. Step 2 is, we are passing this Y through the activation layer, and then on basis of this activation layer, which gives me value between 0 to 1, it is giving me value somewhere around like, let's say 0.6 or somewhere. And if it is more than, let's say, our threshold, which is 0.5, we can able to fire, we will be able to move ahead with this. This much part is clear. So what I'm saying is, when I try to calculate the W1, it will be dependent on the O11, output O21 and O31. That means this O11, this second layer O21 and third layer O31. So all this layer will be responsible when I trying to calculate W1, and that I have written in terms of the derivative. When I'm trying to calculate the radio to the loss function with respect to the weight 1, 11, weight 11. So at that time, I am trying to write simply bifurcate them in terms of the O11, O21, and O31, right? Third layer output, second layer output, and first layer output. And then I can restore. This much part is clear. And what I'm saying is I am trying to refer this term as a Z, and activation function. This Z is passing through the activation function, and this is how it will be able to give us a output to 1, right? That's what I'm trying to say here. So once we understand this, now we will be moving forward. So when I trying to calculate the O21 weights at the O21 level, so what I can write is again here derivative of O21, that is second layer I'm talking about here. Second layer O21, if I'm trying to calculate, right, with respect to O11 here. So how I can write that? So I understood this as a of Z, right? So that will be derivative of this Z, activation Z, with respect to Z, dz, and again that dz, chain rule, same thing, dz divided by what? Derivative of O11, right? I am trying to simply expand O21 with respect to O211. Let me use a different color and try to show you from the graphical perspective. We are trying to calculate the relationship between this O11 and O21, this weights. We understood if I have to calculate the weight for 11, first layer, you have to consider all 3 layers. But now for simplicity purpose, I've even written that formula here, right? Three notations we have written here. If I have to calculate loss with respect to 11, I've written loss will be calculated first with the output layer 3.1, then with respect to 2.1 layer, and then with respect to 1 layer. So I am trying to take relationship just now at this point only. I'm not going beyond that point because again calculating the 3 derivatives will be different. So I will try to consider only till this level. So what I have written here is, so let me use different color and write it again. Maybe red is becoming more prominent. So let me use the color darker one to write it in better way. So I'm trying to write a relationship between the O21 and O11 when I am trying to calculate a loss for the O21 with respect to O11. It will be again dependent on what? So I'm considering this function, right? This function as Z. So it will be activation function of what? Z. This activation function Z divided by dz. Again multiplied by dz divided by O11. I'm just trying to, let's say I'm trying to take the same thing, O21, and I am trying to add just a multiply and divide the term by same thing, which is dz, right? Derivative of Z. In this case also you can understand, right? So when I am trying to calculate this and this activation function, why I'm telling this is really actually happening in the neural networks. In neural networks, we are taking at each and every level weights and biases. Whatever output I am getting, right? Say initially I started with X with respect to W11, it will give me output 11. This output 11 consists of the everything, right? Summation of input, weight plus biases. This is actually happening. Then I am able to get a output of O11. So that is what I am trying to calculate. The second layer output, which will be consist of the second layer output will be consist of O11, previous layer output, right? O11, sorry, consists of this one. So that's what I'm trying to tell here by using chain rule. If I were to calculate the loss function with respect to O21, which will be dependent on O11. So I'm trying to just expand these terms. I'm trying to write it as a function of the activation function and trying to multiply and divide by the same term. If we calculate the same term, if you cancel out, it will become the same equation. So now try to understand what is the beauty here. So what I said is exploding gradient descent means what? Our weights are getting very huge. That means the difference between the old weight and the new weight is very huge. Let's try to understand in this way. that when I'm trying to calculate this further derivative, if I calculate with respect to z, right? So I can expand. Let me again rub some things over here. Now you guys are clear that what is happening over here. dz, this do11 can be written in the form of a of z. That means this passing through the weights and biases activation function, and I'm trying to write it just by multiplying and dividing by dz. Same thing, the derivative of O11 divided by O21 divided by O11 can be written in this way. Again, I can bifurcate this activation function of first term I will keep as it is. Okay. And second term I will try to bifurcate dz by O11. dz by O11. Because z again, what it consists of? Z. Again, weights and biases, right? Weight side 211, correct? Multiplied by O11 plus biases, right? Weights into O11 divided by weights plus biases, right? Weights plus biases divided by O11. That is with respect to 11. Same thing I'm trying to put, but I'm trying to expand this z, because this z is what? Is inputs multiplied by weights plus biases. That is the same form I'm trying to take. I'm trying to understand the layers, right? Layer at weights at layer 2 divided by the output at that previous layer plus biases and with respect to 1. So when I am trying to take this derivative, this entire terms, and let's say at that time o is x, right? And this second term will be constant. If I take derivative, this entire term will get reduced to W2. This W2. Try understand this way. If it get reduced to W2, then I will be left with what? dA by dz into weight 2, right? And this weight 2, now I already got that. Whenever I trying to calculate the activation function, derivative of activation function was lying previously between 0 to 0.25, right? So whatever value is there, whatever derivative will be there, for this value it will be between 0 to 0.25 and then multiply by the weight, right? Multiply by this weight. So how it will go further? It will become like 0.25, let's say. And this new weight, if let's say I am giving as 500, my weights, what I am saying is, if I take a very high weight, what will happen? If I give this side as weight as 2.5, loss function value becomes 0.25, because whenever I try to take a sigmoid function value, it will always be between derivative of the sigmoid function, right? Sigmoid is an activation function. This activation function, it will be always between 0 to 0.25. So whatever derivative I will take, all the value will come between some range. So I took 0.25, and this entire will be reduced to the weight, right? Because this is weight. This is in fact, if you look here, it is weight only, right? This weight we are trying to update. When we are trying to update this output over 1, at that time we are trying to take this weight, right? And this weight is in consisting of what? Weights and biases, weight multiplied by input plus biases. So that's the simple thing I'm trying to do. And if I say that weight is like around 500, let's say I'm taking very high weight and then multiplying by the derivative of the loss function. So again, it will be somewhere around like 125. So my new weight, what will become? Loss formula, what is has become there now? The loss with respect to O21 and O11 is 125. So if I go back again, this 125 value, if I try to put that value in this formula, right? So this, how it will look like, I will tell you. Let's say initially weight was, this was 5. multiply by the learning rate 1 and multiply by 0.25 into 500 is 125. Let's say hypothetically. So that means 5 minus 125. What will the value? 5 minus 125, 120. So my new weight will become 120, wherein my old weight was 5. Just try understand. I know somewhat it is messy. So only thing I am trying to convey by taking derivatives and trying to take the chain rule is whenever I trying to consider the higher weight, let's say this kind of higher weight, 500 weight, and I'm trying to input in my formula, and then when I'm trying to calculate a new weight, the difference between old weight and new weight will be very much different. There will be huge difference. Let's rub everything, and let's try to put these things in back where we started. A simple formula. So I will just try to summarize within 1 minute, guys. I know it's somewhat messy now. Let's try to understand again. I'm trying to update this weight 11, right? And this weight 11 consists of old weight, new weight, consists of what? Right, this consists of old weight 1 minus learning rate into derivative of loss with respect to weight, right? So what I'm trying to simply say is, so do you mess? I'm not able to understand. Yeah, guys, I'm trying to explain it again. What we decided is that whenever I try to, I was trying to just calculate the simple chain rule. On the basis of the chain rule, I went and expanded the things, and what we saw is when we try to calculate with using the higher weights, again the difference between old weight and new weight will be very high, and because of this high weight, the model's performance will be very different. That's what we're trying to summarize here. So I will try to explain you guys again very simple terms. That's what I was trying to tell you here. So if this is my neural, not all three, the simple layer I was trying to talk about. So when I trying to calculate from layer 1 to layer 2 to layer 3 to layer 4 here, and here somewhere was weight 11, and this is O. This is output because this will be output 1, this will be output layer 2, 1, this is output layer 3, 1. So when I have to calculate W1, I have to take the effect of everything. So that's what I'm trying to write in the equation. I will try to write in the equation, and I'll simply give you a simple example so you guys will be able to understand. I will not go into detail of the derivative and everything. I'll try to give you simple example. So if I calculate the weight 11, right? Sorry. Calculate the new weight, right? Weight 11 new. It will be given by formula old weight minus eta divided by derivative of loss with respect to that weight. What I am trying to understand is why I can write this equation using the chain rule. By using the chain rule, we wrote something like that. When I try to calculate this derivative dl by d11, same thing can be written as d by O31 divided by d by O21 multiplied by d by O21 divided by d by O11 multiplied by output 11 divided by output 11. Now this part is clear, I guess, right? I can expand with respect to weight 1 loss function in this way because it depends on output 3 output 2 and output 1. So what we were trying to understand is this all outputs, whatever loss functions are there, these loss functions are in term a complex product of what? Weights and inputs plus biases, right? So what happening is when I'm trying to calculate a new weight at 11th stage, right? New weight. If my old weight is 5, right? I have to calculate new weight. Learning rate I'm taking as 1. And if I'm trying to calculate this loss function with respect to the old weight, and value is coming somewhere, like say around 125. After calculating everything, all the weights and all the derivatives, if my value is coming somewhere around 125, right? Approximately, if I try to insert that value in the weight calculation, what will happen? 5 minus 125, it will be around like 120, and my new weight will become 120, wherein my old weight was 5. So there is a huge jump, right? So when we try to calculate the gradient descent to reduce the loss, okay. This positive side, negative side, positive side. And this was our old weight, let's say here, W11 old. And this W11 old again directly got a jump of, let's say 120. Jump of 120 from 5. So this way, if I am trying to jump with very high weights, so what is the probability to reach to this normal 0 level? Because this is 0, will be very less, right? Probability will be very less. That's what we try to understand from the perspective. So all the issue comes in for exploding gradient descent is whenever I am trying to give a high weights. Why high weights are given here? Because of the calculation we perform, difference of the calculation between the weights is very high, then we'll not be able to reduce loss. That was the entire idea. I think now it is clear, guys, what I'm trying to explain. If I take a huge difference between the weights at that time, that will be called as exploding gradient descent. And by mathematically also, we can prove that using the chain rule. If I try to calculate and expand the terms, then it will be reduced to somewhere around like weight multiplied by the derivative of loss. And by doing that, we can understand that there will be huge difference between new weight and old weight. And if there is a huge difference, means our we will never reach the global minima point. And then if you are not able to reach, my model is not learning and weights are not updated correctly. And this situation is called as exploding gradient descent. I guess, guys, this part is now clear, I think, right? What is exploding gradient descent now? Why it is exploding means there is a huge difference between the weights. And from mathematical perspective also, if you keep on calculating the derivatives by using chain rule, at certain point of time, you will understand that I'm getting very high value for the loss. And that loss value, if I try to calculate using the weight, that is giving me very huge difference. So just quickly ping me now, it is clear, guys. So we understood that by second, let's say for second way, we try to understand using the chain rule and not going into the most complex topic. So we try to understand that why it is creating huge weights and what is the difference. So quickly ping me that whether you guys were able to understand this part or not. Okay. So Ayush, you were saying that you were not able to understand. So that's why again I went ahead and tried to explain it in very simple way. So are you now able to get it? What I'm trying to explain? The simple idea of what you have to explain here is, understand here is, whenever I take a huge difference between the weights, then it will be an exploding gradient descent. I hope for everyone it is clear now, guys. And you are, I think I know somewhere when we were calculating the much complex derivative, we were trying to get it. Yes, sir. Understand once, but I get material, I will perform. Okay, guys. You see why I'm telling you these things is you don't have to perform this calculation. Try and understand. Okay. So whenever you are trying to deal with the deep learning techniques or artificial neural network, you don't have to perform this calculation. But what we have to do is we have to understand that what is happening over here. This calculation, why I am doing that, you should understand that this is the problem with the neural network. And when this kind of problems are happening, let's say vanishing gradient descent or exploding gradient descent, what is going wrong? At that time, you will understand. I think, yes, Ayush is now able to understand, and he's saying that once we get a material, we will get a hold of it. Yeah, guys, you can get a hold of it, or even you can go ahead and try to calculate using the derivative and try to put it the same way that I have put in the calculation. So maybe at that time, you'll realize. Okay. So why I'm taking this exercise is because whenever you guys are able to deal with the different neural network, this the terminology or the way of the work neural networks works, or any, let it be RNN, CNN, or let it be any kind of LLM or the large language model, which is a chat GPT. Now, all the techniques or all the working will be same. The process will be same. At that time also, you will face this kind of issues like vanishing gradient descent, exploding gradient descent, and then how can you handle this exploring gradient descent, and how you will be able to get a better predictions, or how your neural network will be able to learn efficiently. That was the whole idea. That's why I'm trying to cover these things. Hope guys this clears, and we have to also go through at least one project. So I will quickly go to the dropout layer. Dropout layer is very simple. There is no much calculations are there. So it is very simple, and I think you will guys will understand looking at the dropout layer. Dropout layer whole idea is what happening is over here is in the dropout layer. What we are saying is when we are taking like different layers, layer by layer, right? Layer by layer we are performing. At times, is it possible that when I am creating a very huge depth neural network, at times, is it possible that I do not take care into certain nodes? I try to disable certain nodes. In this case, understand this one. If you are trying to look at this node, not all the nodes are taken into consideration where we are taking the training. Even though initially I have created neural network in this way, where I have 3 layers, hidden layers, hidden layer 1, hidden layer 2, and hidden layer 3. And this is my output layer, and this is my input layer. Whenever I am having this kind of neural network, just for the simplicity, we are drawing 3. Maybe there are 100 layers in between. So at times, what happens is when we are trying to train this kind of layer, huge layer, okay, at that time, it is possible that your model may try to overfit. Okay, try to understand overfitting. Your model may try to overfit at that time, or maybe not able to learn very robustly, right? So, and we'll try to understand when I will go to next slide, what is overfitting happening over here. So try and understand that it is not giving you a correct predictions, because you are trying to train a huge neural network, and this huge neural network is not performing some way is not performing correctly. So at that time, what you can do, that situation will be called as overfitting. So overfitting means it is giving you a very weird predictions. Simple terms, try to understand. Okay. So at that time, what you will do, what you can do is you already created various layers, right? And you through the various layers, this forward propagation, back propagation is happening. And because of that, it is computing huge computation. So what if I can do something like this, that whenever I try to take the training of the neural network, some of the neurons I will disable. Like in this case, some of the neuron I will disable temporarily. For temporary movement while training, I will disable some of the neurons, and I will be able to train only on some other selected neurons on one iteration. Okay. First time, one iteration. For one iteration, ITR, I will try to disable these things and will perform the iteration. And maybe for next time, again, I will try to do certain epochs. And at that time, what I will do is whenever I just deactivated certain neurons, I will try to deactivate certain other neurons in next iteration. Let's say maybe this kind of neurons, which I am denoting by the green layer, green color. In second iterations, I am just trying to deactivate certain neurons which are shown in the green colors. So by this way, what will happen is there will be two things will be happening. So I am not trying to take all the features at that time, right? I'm not taking all the inputs. What I'm doing is I'm trying to take all the inputs initially, right? When I am not doing any dropouts. In dropouts, what I'm doing, I'm taking certain out of, let's say, 3 features. I'm taking only combination of 1 and 2 feature and trying to pass and train the neural network. Okay. And I will try to take the predictions. And again, in second iteration, what I will do, I will take a combination of x3 plus x2 this time. And then I will train the neural network. Getting, that's how what I'm trying to tell you. If there is a huge neural network, it will try to overfit. In order to avoid that overfit, we are doing a dropouts. What do we mean by dropouts? We are trying to hide some neurons when training. So first iteration, I was able to hide like the neurons which were shown in red color. In second iteration, I will try to hide the neurons which are in the green color. And then when I am done with the training, then I will try to consider the entire all the neurons again. This entire neural network, and I will consider this as a whole model. Yes, anyone asking anything? Feedback link. Yeah, guys, it is shared. Feedback link will be shared by Amar. He is sharing that one. So that is dropout, guys. So instead of taking entire neural network at a time, I am trying to deactivate certain nodes, and then I am performing the training. Again, in second iteration, I am taking certain other let's say neurons, and then I am doing the training. And end of it, I'll try to test it with the entire neural network. That is the idea behind the dropout. So let's understand this. Very simple example, guys. Okay. And this is not anything complex or no derivative or no calculation. Just within 5 minutes, we will be able to finish this one. So what happening was, this entire concept came into picture, right? And this entire picture, why this thing is came into picture is, whenever I told you that whenever we are trying to train a neural network which is having very high depth, it will try to overfit or show high variance. Significance of dropout, guys. Dropout we're using. That's what we're trying to understand here. What is the significance of dropout? So what we are doing is, we're trying to take a dropout. By using the dropout, we can overcome the overfitting. What do you mean by overfitting? Is my model is not giving accurate prediction, or whatever prediction it is giving are very weird. Okay, so there is an inconsistency in the prediction. So that is called as overfitting in simple terms, or which is called as high variance. Okay, high variance. And because of the high variance, my prediction are not correct or not giving correct prediction. So in order to avoid this kind of situation, I am doing dropout. And dropout is a technique used as an regularization, because I am trying to regularize or trying to penalize my model for doing the wrong predictions. Okay, what is happening? Again, simple picture. Instead of taking all the inputs at a time, I am just choosing certain inputs. Let's say in this case, I am choosing X1 and X3. And then I'm trying to pass through the hidden layer. Even in hidden layer, I'm taking the neurons which are in white colors, not on all the colors. And again, second layer, I'm trying to hide something which are in the red colors. And this red colors neuron will be hidden, right? Red colors will be hidden, and only white colors will be taken, and then the iteration will be performed. And again, going back, this is how the things will happen. And why we need this is because to regularize the neural network. So there are two ways to regularize. One is you can use a L1, L2 regularization, or you can use a dropout layer. So we understood. So dropout layer has become more popular, and this was introduced by, again, the godfather Jeff Hilton and our Indian colleague Nitish Srivastava in 2014, guys. Right? So all these things were started in 2014 by these two gentlemen, and by using this, we were able to penalize our neural network. So whenever it's going wrong or giving various different prediction, we can penalize. So you will say, now I understood what is dropout, and how dropout is working is, I am creating the neural network, but in the iteration while training, I am not considering everything at a time. That means you can consider as an in batch wise manner, right? I am taking the batches, different batches, and by using the different combination of the neurons, I am trying to train my neural network. Trying to train the neural network. That is the simple concept, guys, behind the dropout. So dropout ratio, that is something called as dropout ratio. Let's say dropout ratio is P. That dropout ratio will always be between 0 to 1. Okay, dropout ratio will be always 0 to 1. Within that, we have to give the dropout ratio. So whatever ratio you are giving, let's say in this case, whenever I say these neurons, half of the neurons I was hiding and only half of the neurons I was taking. So ratio is 0.5, 0.5%. So that's how, instead of chain rule, you are using dropout. No, guys. It is not the chain rule replacement. It's not replacing the chain rule. It is entirely a different concept. Chain rule, why we are using chain rule? Chain rule is for calculating the weights. If I am calculating the weights at this level, I have to also consider the hidden. If I am calculating the weight at the level hidden layer 1, I have to also calculate the effect of everything. So that's why we were trying to create a chain, the chain of the output with hidden layer 1, again with hidden layer 2 to hidden layer 1. So that is called a chain. Try to understand. And the dropout is what we are doing is different, guys. Dropout is different. Instead of creating taking all the features at a time, I'm just taking only half of the feature. Let's say my ratio is 0.5. I will be taking only half features at first iteration. I will train my neural network. Again, next time I will take the remaining half, which are shown in white color here, and I will try to train my neural network. And this way, I can efficiently train my neural network with less computation. Less computation power also, because I need to perform calculation derivative, these many derivatives. The way you try to introduce many layers, there will be that kind of calculation will be happening. So instead of that, and when you're trying to create such a complex structure, what happens is your neural network may give you very different predictions. So that different prediction is called as a term high variance. So that leads to a high variance. High variance means your neural network is not performing consistently. So in order to avoid this high variance, we are using this methodology called as dropout layer. Simple, guys. Now clear? So you will again say that first we try to understand what could be the value of the dropout ratio. It will be always between 0 to 1. Okay. Now how to choose the value, which value you will choose at what level? So that can be again given by the two methods. One, whenever you have a higher layers, number of layers are very high. So always try to keep your dropout layer somewhere between 0.5 to above. Okay, that is one thumb rule. And then second thumb rule or scientific way will be using these two algorithms. These two algorithms, grid search CV, and the CV means cross validation. Okay, these are the two algorithms which are available. These two algorithms, what they will do, they will try to take a range of different parameters. Let's say if your dropout ratio is between 0 to 1, can you give me mathematical example for dropout? So there is no mathematical example, sir, because we are not calculating any derivative. What I am trying to do is, this will be like whenever I am trying to train my model, let's say the code will be like this, model.fit. Okay, try and understand. Model.fit is my function where I am trying to train my model. At that time, I will give you a data, let's say xtrain, xtree, and xtest. This is the data set I am providing. At that time, there will be one parameter called as dropout, let's say D. So we have to provide the value for this D. And on the basis of this value, let's say I provide this value as 0.5 because I have to provide something between 1 to 5. Between 1 to 5 at that time, if I am trying to provide the value for this parameter D, so accordingly, this will be happening in the background. So it will be taking only half of the neurons at a time. Then again, next half neurons, and so on for that many iteration. Let's say for 1000 iteration, it will perform this kind of permutation, and then it will give you a final prediction. So that is what is happening, guys. Okay, clear? What is dropout? And what we are doing is, again, see, one is you using dropout layer. Out of that dropout layer, you trying to say what will be the ratio for this dropout between 0 to 1, and how you will choose the value is one, you choose these algorithms and where they will provide you the range, and with this range they will create a loop. They will create a loop. Through that loop, they will try to perform and give you the best parameters. Okay, what will be the best parameters, best value for the P. So that is also possible. And if not, there is a thumb rule. So thumb rule says whenever you are trying to do a high depth neural network, okay, At that time, take a value which at least starting from 0.5 and higher. So the higher than 0.5. These are the two rules. And when, let's say, try to concentrate on this picture, what we did is we took only half of the neural network at the training, but at the prediction time, it will consider entire neural network and it will test. Simple, guys. Clear, everyone? What is dropout? Just ping me, guys, quickly, because this is no mathematics involved here. And this is just the concept, and we have to create only one value for the variable, which is called as dropout ratio. And depending on the dropout ratio, you can penalize your model or a neural network, and then it will be able to give you a consistent prediction. And the concept or the cause here is high variance. If it is giving you high variance, so that is the issue. In order to avoid that high variance, we are using the regularization, and regulation in terms of the dropout. Okay. So try understand that only we are using the combination, different combination of the neuron at the training time, and that combination is again chosen by not us, by neural network, depending on the value. You just have to sit back, relax, and try to understand. It is trying to perform the training, and it will give you the prediction. If the prediction is not correct, again you can try with the different values. That will be the only job you will be doing. But in the background, it will be performing this kind of operation. That's what we are trying to understand here. Clear, guys, everyone? Or any doubts? Or are you guys facing any concept you guys want to understand or ask? I know somewhat heavy topics were there. That's why I kept them in the somewhat in the later part. So, but dropout is very easy, right? Instead of taking entire neural network, we are taking the permutation combination of the neurons, and then we are trying to perform the training, and then we are getting the results. Yes, guys, quickly ping me if you are able to understand dropout layer and then the exploding and vanishing gradient descent, or I can start with the code then tomorrow. We can create our, we go and try to create our 2 neural networks, right? Yes, no, something like that, guys. At least tell me how this will be useful in programming. Yes, guys, I will tell you how this is useful. Try to understand how it is useful in programming. So when I am doing programming, I told you that one code you have to write is model dot understood the concept but not feeling very much confident. Don't worry, guys, you will feel confident when we'll try to create a models further. So why I'm telling you that, what you have to do is, there is only 3 lines of code which is available. Little confusing, I can understand, guys, but only thing you have to understand over here is, instead of using entire neural network, we are using only partial neural networks. The combination of partial neural network, and it will be able to solve your problem. This simple concept we are trying to show you from the graphical perspective. Just forget about all other things. So try to understand, when I'm creating very high depth neural network, at that time we are taking only partial part of the neural networks and training, and then we'll try to combine result of everything. That's how to select nodes to drop out. You will not selecting, guys. It will be done randomly by the neural network. So neural network itself will try to randomly select certain points, which points to be deactivated and which points to be kept, right? So why I'm saying is how it is relevant to programming. So when you're trying to create a program for the neural networks, at that time you have to tell what will be the data. Okay, this is the parameter data. Out of that, what model you are trying to choose, and out of that there will be also whether you want to use any dropout layer or not. And if you want to use a dropout layer, please give me a percentage of ratio. So these are the parameters you have to give while doing the programming. So if I want to give a parameter, then value should be between somewhere 0 to 1. So all that has to do with this coding. That's why we're trying to understand this concept. If you are doing this coding, at that time you should be able to understand that what kind of parameters I have to fill in the coding, and what that parameters meaning is, and how I can handle if my model is not performing very well. So this all things comes under the hyperparameter tuning also, right? Dropout layer is a regulation technique. By regulation means what? as if even if you try to take the example as per its meaning, we are trying to regularize. What we are trying to regularize? We are trying to regularize the prediction of the neural network. Simple, correct? Okay, all right, guys. So no use in starting again entire new code, because I wanted to show even today itself how we can create our neural network. So tomorrow, first thing, I will not create any slides or anything. We'll directly jump into the coding part. We'll create a neural network, one with the structured data, one with the unstructured data, one with the image, one with the table, and we'll try to solve the problem. But still we got like 5 to 10 minutes. If you guys want to ask anything related to the vanishing gradient descent, anything related to the exploding gradient descent, or anything related to the dropout layer, please go ahead and shoot the questions. So I will be able to answer you guys. Okay. Ask question, guys, if you want to ask anything related to this concept, dropout layer, or vanishing gradient, or exploding gradient. Just ask me the questions. Within 10 minutes, I will be able to answer you guys, if you have any pertaining question related to these three topics. No questions, guys? Everyone is okay with the concept? Try to utilize this time, guys, because I will not start with the new topic, because it's only 10 minutes left today. Come on, guys. There are like more than 360 participants are there. I think you guys should ask me certain questions, or at least tell me a confirmation whether you guys are comfortable or not comfortable with the topic, or you need any specific explanation further on this topic. Let's make it somewhat interactive, guys, rather than monotonous. Anything you feel you want to ask, you can go ahead and ask, guys. Yeah, it's complex, I can understand, guys, but you don't have to perform this calculation. That is the beauty of the neural networks. Why I'm giving you these things? Because it should not be the happening the way that you are just writing the code, but you are not able to understand how the model is working, or how the neural networks are working. If you don't understand how the things work, how you can make a use of it, right? If you buy if you buy an iPhone, let's say if you are trying to buy an iPhone, but you don't know the features, so what's the use of using that phone, right? If you don't know any feature of the iPhone. Same way, you should understand the features of the neural network. Then you will be able to achieve the desired result. That's why we are taking all this pain to understand the calculations, understand the concepts. Coding part, so coding part only will do. Yes, coding will only do everything. You don't have to perform this calculation, guys. Not a single mathematical calculation you will be performing. You will just writing the codes. Which language you will use? We will use Python, guys. By using Python only, we will do the coding. So we will be obviously using the, let's say, TensorFlow, Keras. These are the frameworks which are available, and we will doing only in the Python. Using Python only, we will be doing the coding. Yeah, guys, anything else? Who next? Who want to ask anything? What is the main difference between vanishing and exploding? Simple. Vanishing means the weights are vanishing, and exploding means weight are becoming higher. Try to remember in this way. Vanishing means weights are becoming very small, so that the old weight and new weight is exactly same. When there is exploding, means there is a huge difference between the old weight and new weight. That's it. That's the one-liner summary for vanishing gradient and exploding gradient. What else, guys? As a data scientist, we will use coding. Yes, correct, guys. We will use coding, but again, same example, guys. If you are buying a high-end iPhone, but you don't know the feature, what is the use of using iPhone? Same way, you have to know the each and every feature of the neural network, how it is working. Then only you will be able to efficiently create models or any neural network using this neural network for your business problem solving. Anything else, guys? Any other questions? Any feedbacks, guys? Just quickly ping me any feedback, what you feel about these topics. We still got 5 minutes, so still I'm available for 5 minutes. I can answer your questions if you feel that you need a clarification on any other thing, these topics. Make a use of the time, guys. Yeah, attendance link is shared by Amar, guys. He shared it. Maybe Amar, you can again share it in the common chat box. Yeah, Amar has shared it, guys. Attendance link as well as the feedback link. Quickly, guys, anyone would like to anything, ask any question, any query? Can you give us a roadmap to take career from non-computer science engineering graduate? Yeah. I will give you a roadmap. In material, I will provide a roadmap. If you guys could remember, in the beginning session, I have created a roadmap for the deep learning as well. Let me check if it is available in today's presentation or not. Most probably, I have deleted those slides and explained complex topic in simple way. Thank you. Okay, thanks. Thank you, Sailesh. This is really motivating, but I need to hear it from some other people also, that whether they are feeling difficulty or whether they are able to follow the presentation or the concepts. So let's go back and try to understand if I have a path over here somewhere. Maybe I will be able to display you right now. Okay, guys, this is the path. Okay. Subject is really interesting. Yeah, guys, correct. Really interesting and as well as complex. But if you try to analyze it in slowly, then you will not feel the complexity of the topic. Okay, guys, this is the complete roadmap. What is the working of Azure, Amazon Cloud in ML? Okay, guys, let's try and understand what is the role will be played by the cloud or Azure. Okay, in this case, Amazon has this AWS cloud, and Azure is from the Microsoft, and again there will be GCP like Google Cloud Platform, which they are providing. Will you share any notes? Yes, guys, I will share all the notes, all these notes and all the codes, everything I will share. So try and understand what cloud is doing. Cloud is giving you frameworks like this kind of frameworks. Let's say PyTorch, Keras, TensorFlow. I'm not, guys, I'm not created any WhatsApp group. What we are doing is, whatever notes will be shared, that will be shared through the LMS portal, Learning Management System, and that will be shared by the ExcelR group, backend team. Okay. So all these things will be through the portal, not through any group or anything. So try and understand, guys, whosoever asking what is the complete roadmap. The roadmap, if you can say comment back, I think this roadmap will start making sense now, because on day one we try to understand this, and I am sure that most of you may not make sense at that time, but here it is the real roadmap. We are still at the stage of first pillar 1. Okay, so we are trying to understand the neural networks and what it takes, the Python, somewhat statistical concepts. Okay, and then this kind of frameworks, PyTorch, Keras, TensorFlow, this K-train and everything. So once we understand the working of the neural networks, then only we'll be able to understand the convolution neural network. And for convolution neural network, this kind of different models are available. Okay, so they are working on the same concept. They are working on the same concept, but the basic understanding is same. Only the somewhat functioning is different from the neural network. Once you guys are able to understand artificial neural network, you will be able to gain convolution neural network, which has only certain different functionalities apart from the basic functioning. And then you will be able to understand what is RNN, recurrent neural network. And for recurrent neural network, these kind of topics are there. Different models are available. You don't have to understand architecture in detail, but if you are able to understand what is the use of which model or what kind of concept is, like say LSTM is there, BiLSTM is there, BERT is there, GPT is there, right? So these kind of models are there. So what is the use and how they are making difference, that you can easily make out. So this is the complete roadmap, guys, for deep learning. Even you are from tech background or non-tech background, these are the must things which you should learn or understand. So coming back to the question where we are speaking about what is the use of the cloud or cloud or let's say the cloud services or Azure or GCP, they are giving you a platform where all these libraries are installed and certain pre-trained functions are there. So you can directly start writing code and deploy the models there. They are mainly used for the deployment. Okay, for the deployment, we are using them. Deployment means, guys, you can, because model is nothing but a programming language, right? A programming file. So how a end user can use that? For that purpose, you have to connect to your end user to your model, right? Your model. So that platform is given by the cloud. Okay, or even for any engineering projects, whosoever want to use your product, so that will be made available through the cloud. So people can access your models or neural networks to solve their problems. I hope, guys, this part is clear now, and then we are already done with our time. So we can conclude our session here, and tomorrow we'll directly jump into the coding for the neural network. So hope you guys enjoyed this session. This is really interesting, guys. If you try to understand, I know certain topics are complex, but try to gain some clarity, then it will make sense, and then we'll enjoy these topics. Thank you very much, guys, and see you tomorrow then. Bye. Amar, I think we can conclude this session now.
Yeah, sure.
Yeah, thank you, guys.